Well, hi, good morning and welcome to my shop. But first, I'm letting you look outside in my backyard. That's snow falling. Son of a gun. More snow. But on the other hand, here's this radio. So, what am I going to do about this radio? Okay, let's do a quick review. Let's start off with that. Where are we at with this radio? Still appears to be no local oscillator. Changed one transistor, had essentially no effect on anything. So I think I'm left thinking about the components around where the local oscillator circuit is on this board. I think I'm going to have to poke my way through all these little components one at a time very carefully and try to figure out if something is open, shorted, or just way off. I still have that mysterious 0 volts. Still have the mysterious 22K resistor, which doesn't appear to be there on the board. Maybe a different value is on the board from the 22 that's on the schematic. So there's some variations between the schematic and the board here. Let's take a look at the schematic here. Okay, so I changed out this transistor. It seemed to have really no effect. I know I commented that it seemed a little stronger when I was working with the video. I don't think it's any stronger than it was. I think changing this transistor has had no effect. So what I think is happening here is the antenna signals coming in, let's say at 100 megahertz or so, regular FM signal, getting amplified here, getting mixed with a local oscillator here, and from there it's heading out on this wire, mostly the IF frequency 10.7 and probably a few remnants of other things that are coming out of the mixer. That's my guess. What I see here when I look with the scope is basically the same thing I see over here, only stronger. So this looks like it's amplifying the incoming signal fine. What's happening is, again, the local oscillator doesn't appear to be affecting it any. It doesn't seem to be present. So I have done some rudimentary testing of some of these parts. I shouldn't say rudimentary. I've tested the diodes. I've tried to prove these capacitors to not be shorted. I had some varying responses with that test. Now, some of this I didn't put on video. Another interesting thing, maybe we'll start with this interesting thing I noticed, and that is the plates. Let me back up. So this is the tuning capacitor here. This is the trimmer for it. Likewise, this is another section of the tuning capacitor here. That's the trimmer for it. And down yonder here is the rest of the tuning capacitor. There's 4 sets of plates. The other 2 sets are here. This is clearly for the AM radio. Look, AM antenna. I mean, it's quite obvious what's going on here. When I check for these plates to not be grounded, that would be up here on this line here. On this line here, I'm looking for the resistance, the ground. I think I have my answer. It's going through this coil. Is the same thing going on up here? I think I have the answer. Maybe not. Two of them present short circuits to ground across the tuning plates. And it's a test I've never done before. I've never given it much thought. So maybe that's, I think that's an unimportant observation for now. But just keep it in mind that 2 sets of tuning plates on the capacitor appear to be shorted to ground. Appear. So I think I really got to get suspicious about this part. The 6.8 resistor, is it really in there? The 470, what about the 22? That's here. See, it says 22, but I can't find the 22. I think I'm just going to need to just take my time and go through all these parts one at a time. But if we just think about the oscillator for a minute. So for the oscillator to work, it needs a couple of things. One, it needs a resonant circuit. And it needs some way of feeding back an amplified signal from the resonant circuit back into the resonant circuit. Obviously this transistor is what's providing the boost, the kick, to keep the oscillator going. This coil, in conjunction with these, well, all three of these capacitors, is going to set up an oscillation, these two being adjustable, this one being tunable from the front knob. I was going to say these are parallel right across this coil, but they're not. There's a capacitor down here. You know, I just realized is the value, yeah, 0.01. The value is written there. 12, probably 12 picofarads, 68 picofarads, 20 picofarads, 5 picofarads, very, very small capacitors, but not this one, 0.01. This is a biggie. Here's another biggie here. Does that matter? Are these bigger ones more likely to fail? I don't think so. I think these are all ceramic capacitors in here. So, you know, maybe L3 is open. Maybe this resistor doesn't exist. Maybe they put this resistor in afterwards because L3 kept opening. And they decided to bypass a bit. I don't know. If I should be able to read from, you know what, I should be able to read from this point to this point, anywhere in here, and read this resistor. Why don't we try that? We'll try to find this point. Oh my gosh. You can assume that there's two large coils I can see, and this is one of them, and this is the other. And these are open. These are on the schematic. They're just individual coils. So these are probably the two I can see in there. One of them, jeepers, can I just put my lead right on the wire? This bare wire coil, so I can get at these 2 points easily. Quickly, let's read both these. Wow, I can see the wire there. It's not burned out. I can see it. Hey, there's another one here. Oop. Oh, that changes everything. There's two visible coils in there, and now there's this one. I don't know. Let's poke around. See if we can find this 6.8. How are we ever going to read a 6.8 across a coil? I'm going to read it as a short through the coil. I have to fire a signal in here and look for the signal across the coil. Haven't I essentially done that? Have I not essentially done that? So this is kind of interesting here. Look at this. So this is the output. So on here you would have a 10.7 AC modulated, FM modulated signal at 10.7 here. I wonder if this is designed to grab the peaks and pop them into this circuit here, essentially pulsing the resonant circuit here. And that's the feedback. Pulse, pulse. Maybe that's how this is working. I mean, why do you have a diode in here? So it'd be interesting to scope some of this. You could scope the other side of this diode and see what is being presented to this line. This line is easy to find. It's one end of this coil. This coil is probably one of two visible coils. And the diode's easy to find. A 1N60, and this one is a 1S85. Now one of these two is black. So I'm going to research that for a minute. I'm going to find out if I can identify the diode based on its color. If by some chance all of them are the same sort of are black like that. And yeah, that's what I'm going to do. And then we're going to poke around right in this area here. Okay, that sounds like a plan. Okay, so a little bit of research has kind of opened my eyes to something here. So this diode up here, the 1N60, is just a common diode. It has its own characteristics, but there's nothing special about it particularly. So maybe it is doing what I'm saying. It's pulsing in the necessary charge to keep the oscillator going here. This one is quite a different diode, a 1S85. So this diode is commonly used, as I read, in RF circuits. It's reverse biased, and in doing so it can be operated as a varactor, which is a variable capacitor. So as you apply more pressure to it in reverse, you know, the depleted zone gets bigger, and I guess the capacitance drops at that point, I would imagine. So the capacitance is small here, it's in picofarads. What exactly this is doing, you know, I would guess it's a compensator. That's a terrible guess. Usually you're compensating against temperature. This thing I don't believe is temperature compensating at all. So I don't really know what it's doing. This is the black one. I dare not change this out because I don't think I have something like this. They're not necessarily all black like the one that's in this radio. Some of them look just like an ordinary glass diode. This guy up here, by the way, is a germanium diode. That means it's just a little more sensitive to being burned out, but I tested this one. We're going to test them again, because now this is critical. This looks like the guy who's keeping the oscillator going. Why don't we just go right after this one, right away, the glass one. Yeah, let's do that. Okay, the glass one. So neither of these are in easy spots to get to. It's down in there. I can only get one terminal from the top. I'm going to have to sort this out on the on this thing. Figure out which pins are which. So I will attend to that, and then we're going to test this guy. Okay, well, it only took a second because I've already done this before. So I have the two diodes marked here. This is the black varactor, and this is the glass one here. So it's just between here and here. We can do this right now. So what I'm going to do, we're just going to test with an ohm meter first. Maybe not an ohm meter. We'll put it on its diode test setting. Let's just make sure something. Allow me to grab a diode. Here's one. One direction we should be reading the reverse resistance. Normally quite high in a diode. The other direction we should be reading the voltage across the. There we are. So that's in millivolts. So it's 600 millivolts. Whoop! What happened there? 600. Just bad connections. So this is telling me the voltage drop across the junction is 600 millivolts. That's perfect. The resistance the other way, I guess, is beyond the range of this to show. So that's a really good diode. Now let's try it in here. Bearing in mind it's in the circuit. We'll take the readings, and if they're weird, then we'll look at the circuit. So it's between here and here. Between here and here. Oop, look what was coming up there. Okay, so 260 is the forward voltage drop on a germanium diode, 260 millivolts. The other way we'll probably see some kind of resistance. Oh, okay, I don't know what's going on. Now it is in the circuit, so 481 millivolts. Germanium diodes aren't all that great. They aren't that bad. There should be like at least a 1 to 10 ratio, I think, between the forward and reverse. So let's try that. So I'm on the 20K scale. I don't know what to expect here. 450 ohms that way. Again, this is in the circuit, so this could be totally invalid. 460 ohms both ways. Really? Now that's interesting. I get the same resistance reading in both directions. It's almost the same. .428. So a little bit different, but not much. So it could just be because this thing's in parallel with something, and I'm really kidding myself doing this. Okay, let's go back and look at the schematic for that. Okay, so first of all, when we're reading across here, we're reading across this capacitor. A long ways through this transistor, kinda. Oh, long ways. Oh, that's interesting. So we're reading through this coil, and then through this coil and resistor. So this thing is really badly shorted out, so to speak, by the components here. So I don't think my test was very valid. That would also explain why we get the same number in both directions. The diode's doing nothing, basically. Oh, so what's that telling me then? That tells, if this is true, then I'm reading the resistance of these two coils in parallel with this relatively large resistor. These two coils in series are adding up to not much. What were they adding up to? 260 ohms. What was it? I'm going to repeat the measurement here. Just hang on a sec. 420. So say a little over 400 ohms. So if this coil were open, then we'd be pushing the current through this resistor. There wouldn't be any 400 ohm reading, unless it's this. Leak here, not likely. A leak here, not likely. This not likely a problem there. Oh, wait a minute. Have I been skipping? I've been skipping through this capacitor down here. Yeah, this capacitor is making what? So what have we gotten out of this? Have we proven anything about this diode? I don't think so. I don't think we proved a darn thing by doing that test. Could change out the diode, could lift one leg of the diode, could put a different test onto this. I've got another unit I can test this with, but all this stuff in parallel with it. Well, we'll try that for fun. Yeah, I don't know. I don't know what else to try. I'll try another instrument here. Hold that one on. Let's see what it thinks. It thinks it's a capacitor. No unknown or damaged part. So this test is invalid. That's all that's really saying to me. Okay, what if we the oscillator is not oscillating, it's pretty hard to find out where the oscillator is stopping. It's stopping everywhere, right? It doesn't oscillate in part of the circuit and not in the rest. It's just not oscillating at all. So anything involved in the oscillation could be bad. If we look, if the diode is doing the right thing, then on the far end of the diode there should be we should see some of the signal that we do see. Some of the signal we do see. That doesn't even make sense. Doesn't even make sense what you're saying. Oh boy. Okay, well, I'm making less sense than normal. That's really getting down to the bottom. I'm going to stop for a while here and ponder, because I really don't know how to approach this. Okay, based on my philosophy of when you don't know what to do, just do something. Just do something. Let's just look at, use the scope here. And we'll take a look at what's on the top of this diode, because the wire is exposed from the top here. I can get at it. So just for fun, we'll take a look. Just make sure everything is copacetic here. Now, I do not have the signal generator running. It's not even connected. Power on. Okay. 122 volts. How come it sounds louder every time I do this? No, there's still nothing. Okay, now we're going to try to look with the scope at what's on the output side of that diode. In other words, if my thinking is right and it's taking little shots into the oscillator, maybe we can see those shots. No, we can't. There's no oscillator shots to see. That's luck, right? This will probably affect the radio too. No effect. Nothing on the screen. How come nothing's on the screen here? There we are. That's better. Scope is as sensitive as it will go. It's showing absolutely nothing. Is that nothing? It's on AC. Well, there's a DC voltage there of some significance. About one division, about 10 volts. It's about 10 volts there. But no signalation at all. Nothing. Now, I guess conceivably all we should see there is the local oscillator signal if there was one. And maybe we shouldn't see any of this, what we hear. We're not really hearing a signal, we're just hearing noise. Let's put a signal in here because I think I'm missing the point. Okay. Danger on the chassis now. Well, maybe danger now on the chassis. So this is going to put 100 megahertz signal into this radio. And we want to see a piece of it show up on the far side of that diode. That's what I'm hoping. Well, I don't know why I'm hoping that. Nothing whatsoever. Okay, so there was a technique I was using to spot the tuning point. It was somewhere around here. There's just no indication whatsoever, of course, in the radio itself. Nothing whatsoever on the scope. The scope made us insensitive as possible. Now it's maximum sensitivity. Oh, that's interesting. So there's some kind of weird tuning effect there. Okay, so this is probably where the signal is 100. That's about right. That all makes sense. So now we do see the signal on the output side of that diode. What's the significance of that? Just to be absolutely sure, I'll turn the strength up and down here. Oop, what happened? Okay, so I'm affecting the camera you're watching this through. So that change on the scope is the camera changing. Can you believe it? So there you are, up and down. Just from putting my arm in the view. A lot of weird things happen with these video cameras. Okay, we've gotten absolutely nowhere. Still convinced there's no local oscillator. If I had a 100 megahertz, I do have a 100 megahertz oscillator. I was going to say I could force in my own local oscillator signal and see if the radio comes to life as a further verification that that is what is wrong with this radio. And I do have this guy here. We can actually use it, I guess, as a fake local oscillator. Sounds like that's got so many problems in itself. They would probably never be sure of the result from something like that. So what does this mean? We see, basically, I'll see if I can speed this up. We'll get a look at the actual signal here. Yikes. And I'm not going to be able to, I don't think. There it is. There it is. Okay, just clean it up a little bit here for you. Again, this is really tricky to do on a camera. So that's about it there. Does actually seem to be a little out of focus. So I see a steady signal here and some funny stuff here. I don't know what to make of any of that. I'll tune the radio a little bit. Yeah. So that's a maximal signal. I'm pretty sure this is what's coming right out of the signal generator. This is not the local oscillator. What we would expect to see here is a very, very powerful local oscillator. Also, if we were seeing the local oscillator, if I tune the radio, I don't think it would go up and down like that. It's even remotely possible that this diode is where the mixing takes place between the local oscillator and the signal. I believe that the mixing has to occur through a non-linear device. So either you've got to take a linear device and operate it non-linearly, usually by pushing it beyond its limits, or you introduce a device that has non-linearities. I guess a diode would be a choice. I don't know. Apparently, I say I don't know an awful lot, but I don't. So I'm still really stuck here. I could go ahead and replace this diode. It's a low risk, I think, this particular one. Don't believe there's any benefit to come from it. You know what? If this diode's working, there should be a different voltage on either side of it. If it's shorted, it would just be the same on either side. The diode may not be biased in a normal way, or biased in a way. How am I going to get at it? To the chassis from either side. Voltage, yeah, to the chassis from either side. It's dramatically different. 0. So you get a 0 here. Hey, there's no 0 there. What's changed? Wow, something a little different about this. That used to be a 0. That used to be a 0. It's supposed to be 2.4. It's not a 0 anymore. What else has changed? It's 11. Wow. That's a good spot there. What is that spot? That's one of the 3 pins. That's the base. So I inject a little noise here into the collector. Hear that? I do the same thing in the base. You know what we hear. Boy, I think this transistor has come to life here because this voltage is there now. Okay, why is the radio not working? Is it because I have it tuned to a signal? Is that what's doing it? So, oops, I didn't mean to turn it off. Just checking the volume. So you can hear the automatic level working when I hit the bass. So what kind of signal's on that bass? What should be on that bass? It's all about the bass. Well, let's take a look. This will probably be too much for the radio to take. Cover your ears. So that's the collector. I'll let you look at the scope here. Don't know what to make of that. And this is the bass. Hard to get it to trigger the level so low. Tune the radio back towards the signal. Okay, so that's nice. I like that. Okay, so that was me changing the output of the signal generator. Turn it down, we don't need to listen to so much hiss. So that's what's appearing on the base of that transistor, and that is the signal coming from the signal generator, which would be the FM station. That's beautiful. It's not doing any good though. Not without the local oscillator. I thought about whether there's a chance I'm entirely wrong and the local oscillator is actually on the other board. And what's coming off this board is just the this. It's just the FM radio signal itself. That would mean you would find it strong on this wire here. It's there, but it's not strong. So really what you want to find here is a 10.7 signal, not a Yeah, okay. Wow. Okay, this is just teasing my brain to death. I'm just about the point where you just got to go in and start changing out parts here and there. Yeah, maybe there's a multiple part failure in here and I'll never be able to think it out. Because the behavior is so strange, I'll never be able to, you know, until I replace the 2 or 3 offending parts, if that's the case. Okay, I'm going to stop and think for a bit. Okay, so I got going on this process, and right away I realized, oh my gosh, I've really overlooked something I need to check out. And it's because I've gotten something confused in my head here, which I can't seem to get out. A little hard to see, but there's a little coil right here. And I keep looking on the schematic and thinking this little coil is the output. This is the input. The output coil is this guy, and I've just been ignoring this big, tall, gigantic can here the whole time. This guy can be tuned. The primary is part of the oscillation circuit, I believe. So maybe by tuning this, I can trigger the oscillator to come back in. Maybe that's all it'll take. Maybe. So that's what I'm going to try next. I'm going to try tuning this. Now, there's going to be a top and a bottom on this guy here, and they've got tape over it, which is kind of interesting. It's the one they taped over. As I was saying, this could have been, you know, this circuit was built on one bench by one person. And perhaps what they did was, as soon as they finished the tuning, they put tape over it. And then we'll go on to the next bench, and the messages, leave that alone. Well, I'm not going to leave it alone now. So either go in through the bottom here or down through the top. You reach the primary. Is there any way to tell? Also, you know what else this says right on it? 10.7. It has 10.7 written right on it. Isn't that something? Doesn't have anything else written on it though. Okay, so if I'm tuning the secondary, what I've kind of found about these transformers in my own mind, I'm not sure this is true, when you tune the primary, you tend to alter the resonance of the circuit involved, and when you tune the secondary, all you tend to do is just to increase the throughput, you get more output. I'm just going to have to guess, I think. There's a really tiny little slug in there. See what I got for that. Yikes, it's really tiny. Much smaller than that. Yikes. Smaller than that. I think that's got it. Ooh, wow, it's really... Now I'm using a weak plastic tool here. These are lousy for doing this because, as I've explained so many times, when you start turning the handle, if the slug doesn't turn, you just load tension into the plastic here, and then the slug will jump when it breaks free. There it goes. Okay, so I've loosened it up anyway, but there still is this problem. At least it's loose and turning. Let's try the other one now. From underneath. There we go. Yep, it's loose and turning. So if I were a primary coil, where would I want to be? Hooked up to the top slug or the bottom slug? Personally, I would go for the bottom slug if I were the primary coil. Okay, so what will happen now? What if I'm tuning this thing and all of a sudden it breaks into the local oscillator starts up? Well, I could detect it on the SDR. This might be a smart move. Set the SDR up to detect this. The radio sound itself should change dramatically too. So I think I could find it just in listening to the radio. But bear in mind too, as soon as I turn that slug, you know, one full turn, there's no coming back. I'll never get it back to exactly where it was. No matter what I try, it's not going to happen. Put a flag on here, count the number of turns, all that stuff. It's never coming back exactly where it was. So this is a bit of a Hail Mary here. Definitely a bit of a Hail Mary. I guess we need this on to make this work. Also, if we have the signal generator tuned in, we should immediately hear. Well, it depends where the local oscillator is. What am I talking about? We have it tuned in terms of the front end. Here we go. That got quieter, so hold still, radio. Oh, don't tell me it's a one-way thing. Oh no. Whew. Cams out really easily in this direction. Tune it back up. I must have gone by where I started by now. You know what? I don't think I'm in there grabbing it. Son of a... Okay, I need another... I need a more correct tool to do this. Oh my gosh. This is even worse in terms of... Okay, that's really in there now. Look at how far I can turn this, and the slug doesn't move. All that. Am I supposed to get louder? I'm able to rotate this almost 2 full rotations while this end sits still, and this thing just, it's going to break. I'm complaining about my tools. Is this one a little stiffer? I think it's bigger. Oh, we're still in there. Quieter. Okay, the loudest spot right around here. We'll assume that's a good spot, believe it. Now we'll try the other. So the theory was that was the secondary, this is the primary. That's the theory. I think it's a bad theory. Let's think about this. If this is... So is that can't be 10.7 I hear coming and going, is it? This is a 10.7 resonant coil. It shouldn't pass 100 megahertz. Pass 100 megahertz a little wee bit, and if the 10.7 signal was there, it would blast through. So without the 10.7, I can still pick up crap coming out of here. Okay, a little musical interlude there. Yeah. Okay, so this clarifies a lot now that I've sort of woken up to the fact that this is a 10.7 tuned transformer. So we know, there's no question, what's coming out of here should be the 10.7 IF signal. And then there's some kind of mixing going on. I'm theorizing the mixing is in this transistor, it could be in this diode even. Somehow the local oscillator is getting mixed with the incoming signal in this area, and out is coming, well, on this line would be all kinds of stuff. Would be everything from the original signal back here to the IF to 200 and potentially up around 200 megahertz could be sitting here. So 200 megahertz has no hope of doing anything in this coil. It's probably killed by this capacitor or this one. So then we're left with the original 100 megahertz and the 10.7. Now that's a 1 to 10 ratio in the frequency. So once again, you could easily kill the 110, or the 100 coming in here, and that would leave you with the 100, the 110 would be killed, leaving you with the 10.7, which we should see here. 10.7. So I can do a frequency check on the scope, but I really think I've done it already, because you know, I've tried to pick up 10.7 here. I've done so many things. Tuning this slug really didn't do anything except increase what you could hear coming out of the radio. And the radio is also incapable of passing 100 megahertz through the IF here. It's just not capable. So what am I listening to? So I'm listening to some noise coming out of here. I've never heard the signal. I've never heard the signal, and my signal generator is producing an FM signal. I've never heard it. And what we would hear is a 5 kilohertz tone coming out of the speaker. You know, I'm going to change that to 1000, because if it does come out, it's just a little more pleasant at 1000. So there's absolutely no detection occurring, because there's nothing to detect, because there's nothing making it into the IF at 10.7, because this oscillator is not working for reasons I have yet to discover. It's possible that changing this transistor has simply introduced another bad transistor. That's possible. Very unlikely though. So I don't think I'm going to want to go back here. Now we're seeing a voltage appear here. It used to be a 0. Now we're seeing a 1.3. What is going on there that this is coming and going? How can you have nothing there at one time and something now? What's going on over here I don't think relates to what's going on in the oscillator. We're going to just guess that this diode is some kind of compensatory diode pushing on the frequency of the local oscillator a little bit to correct it for something. I don't know what. That's what we'll assume that diode's doing. I should test this diode again. Even though it's used as a varactor, apparently, I don't know for sure it's being used that way here. It would have to be reverse biased. But it still can be tested as a diode. I should double check this one. And certainly if it's shorted, that's got to be a problem. I did check it before. We'll check it again. Check this diode again. I found this resistor, 470. It's in there. I haven't spotted the 6.8 yet. What's this? C13.01. What's this? X2. That's interesting. Why didn't they put a 0.02 there? This means times 2. This means there's 2 capacitors side by side making up this. 2 physical capacitors. Okay, I'm going to go look for that, because I know there are a couple jammed right beside each other. It just helps me locate things. Oh my god. Okay. Okay, I have found something just out of the blue here. Let's see if I can show you it. Now this radio is on right now, so I'm afraid you're probably going to see my heartbeat in this image. Let's see if I can just steady the camera a little more. Okay, it's just a little further up to get it in focus. There we go. What's that? Is it supposed to be soldered in here? Supposed to be soldered in over here? What is that? I think it's supposed to be soldered onto this. I may have messed up when I was in here soldering. So we got to be careful now and get this guy soldered to the right thing. It's isolated there. I'm pretty sure it's just floating out there on its own. Yeah, you'd have to guess it's part of this blob, the big blob there. Okay, so let me. Maybe it is connected. No. Okay, and it connected with this little lead here. Let's tune the radio. There you are. It's my little happy dance song there I'm singing. Okay, let's apply a little solder to that. Man alive. Bingo. So, what does this mean? This means it could be the transistor was defective that I replaced. I put the new one in, I soldered it in poorly, and ended up just with the same kind of problem. Or originally there was a solder problem here of some sort. Very unlikely. I think we can go with the story that the transistor was bad. I put the new one in and I didn't get it soldered in right. Now before we go with too many stories, let's fix this. Make sure I'm not excited about nothing. The glow. The glow. Yeah, I'm really beside myself now. Okay. Persistence has paid off. Let me get rid of my glow box. You never know where the solution is going to come, but for sure when you're having really weird stuff, it tends to be this kind of thing. Okay, radio's definitely off. Power's off. Let's solder this guy properly. See, with my eyes, it looks fine. If you look closely with your eyes, it looks suspicious. But only under the magnifier can you really see what's happening. Okay, I think I've included that part now. Oh man, if this radio works. Hot diggity dog. Here we go. Everything out of the way. Everybody, all fingers crossed, please. We need everything we got here. Switch on. Come on, baby.
Put some pop in your weekend. The Weekender.
I just did.
On Barry's hit music station, Fresh 93.1.
Wow. Okay, you know what I'm going to do? I'm going to stop right here because I got a lot of good stuff in my head now. I'm feeling great. I'm going to go face the snow that's falling. We have 10 to 15 centimeters of snow coming. Today, in the last 2 days, each day for an hour and a half, I hacked ice off my deck. 1.5 inch thick ice with 2 feet of snow on top. 3 hours of getting my deck clear, and it's covered in snow again today. But you know what? I got enough goodness out of what happened here today in my shop that I can stand up to it. Thanks so much for watching, and what we got to do from here is just tune up the radio now and get it sounding, get it receiving well. Wow, okay, I'm so excited. See ya!